Hello and welcome to TidyX episode 100! Woo! TidyX is a screencast where we go through and explain how our code works. My name is Ellis Hughes, and you can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSP Patrick. And you can find Tidy Explained on Twitter at Tidy_explained. Or you can find us on Gmail at tidy.explained.com. Or you can take out an issue on the GitHub repo, or you can like and subscribe on the YouTube channel and drop a comment or question below. We've had lots of comments and questions over the past few weeks, which is really awesome, and we appreciate that.
We really appreciate it.
And we also have a Patreon page. If you enjoy the work that we're doing and want to support us in any way, we're super grateful for that. And we've had some patrons over the past few weeks, and so we're super thankful for that. And 100 episodes, we've made it.
We've made it. Triple digits.
Triple digits.
All right. Yeah. No, we've had a great time. Great time doing this. We've gotten some great emails over the last, 2 years in a month or so. Mm-hmm. So 25 months.
Is that what it is? 2 years in a month? Yeah.
Yeah. So love hearing from you all. If you like what we're doing and want to support us, we really would appreciate it. But let's get on with our episode now that we've been blathering for a minute and a half. So we have been doing a series on sampling, simulation, and intro to Bayes. And we are talking about Bayes. Last week we talked a little bit about some applications of Bayes. And how you can conceptualize Bayes, and how the way it works is you have an idea and then you apply data to it and update your understanding of it based on this new data. Now we're going to talk a little bit more about the actual application and give you some more real world examples of how this works. So let me share the screen. Patrick, do you have anything to talk about?
No, last week we talked about some of the general theory and concepts, and we showed some of the classic Bayes problems. So this week we're going to actually show it live in an example of updating inline. So as new information comes in, you update your data, or you update your knowledge about the situation, and we'll show you how you kind of continue to progress forward and down the road with that. And we're going to do it in an instance where the outcome of interest is a proportion. It's a probability. It's a binary outcome of successes and failures, or successes divided by the total, right? And then in subsequent weeks, we'll work through counts and rates and distributions, normal distributions and things like that. So in order to set this up, we begin with a problem. And the problem is we want to add a new basketball player to our team. And so we're going to hold some tryouts. And we want to determine the field goal percentage of the players that are trying out by observing some shots in this special drill that we came up with. And so what we know is that on average, tryout players who we've observed before come in, and their performance on this drill is about 13 out of 20. So about 65%. And so we observe a new player comes in and we're trying them out, and they go 16 out of 20, right? So they're an 80% success rate relative to the 65% success rate.
Next LeBron.
Hopefully, right? We're going to find out. Let's create just a little kind of simulation of what this player's data might look like. We load up Tidyverse and we create a tibble that shows each shot number and then the subsequent outcome, whether it was a success, a 1, or a failure, a miss, a 0.
Boom. Got that right
and
there.
We can check the field goal percentage of this individual player as 80%. So it's 15% better than the quote unquote population average. And what we want to know is how confident are we that this individual is actually 15% better than the average player that we see. So we set up our hypothesis, which is trying to answer the question, what's the probability that this player is a 65% shooter, or better than a 65% shooter, rather. So we calculate this by looking at the observations that they got 16 out of 20 given that our null hypothesis, our tryout player, our average tryout player, is a 65% shooter. So in frequentist statistics, which we talked about last week, the difference in theory between frequentist and Bayes, this is asking what's the probability of my data given my hypothesis, given the underlying hypothesis that average players are 65%. So we set that hypothesis up here on line 45. And let's first start by calculating what's the probability of observing 16 successes out of 20 attempts, given we have this hypothesis of an athlete being a 65% shooter. And we run that, we get a probability returned to us. We can take it one step further in frequentist fashion and calculate a p-value. The binomial test function is a helper function that runs a binomial test over a proportion like this. And so again, we're saying we have 16 successes in n equals 20 shot attempts. Our hypothesis is that the probability, the true probability of success is 65%. And we want to know what's the probability that 16 out of 20 is better than our hypothesis of 65%. So it's an alternative hypothesis is greater than.
Well, it looks like we had some technical difficulties, but anyway, Patrick's now back, and we were talking about the alternative and how we're looking at the probability that we will shoot something greater than H1, which is the probability of shooting 65%.
Yeah, that's right. So it wouldn't be a 100th episode without technical difficulties. So the binomial test, again, it's just a helper function. In classic frequentist fashion, we pass it the number of successes, given the number of attempts, given our hypothesis, which in this case is 65%. The alternative here can take on three values. So we can be checking that what we've observed is greater than our hypothesis, is less than our hypothesis, or we could do a two-sided test, which is basically saying we don't know if it should be greater than or less than, so we're not committing in either direction. In this case, we're looking at the probability. Yeah, in this case, we're looking at the probability that the person that we just observed is actually better than the average population. And when we run this, we get our successes and our trials, and we get a p-value, which isn't significant, but we're dealing with small samples here. And you can see the 95% confidence interval stretches down to 0.598, basically we'll call it 0.6, which crosses our hypothesis. Our hypothesis is 0.65, so it crosses over that. So the p-value is basically telling us that we're uncertain that what we've observed is actually better than the average. And if we didn't want to run the binomial test function, we could use the p-binomial, which we talked about in episode 1, and that's just going to also return the p-value for us. So we basically want to know, did we hit 16 out of 20? It's set to 15 there because it's actually like a 1 minus, right? So it's not intuitive to remember, but it's just what it is. And then set lower tail to false. This isn't that cool. This is frequentist statistics, and we're like, whatever. But what we really want to do is use our prior knowledge and what we've observed and answer the question, what's the probability that this player is better than the average given my data? So what's the probability of my hypothesis given my data? So we set up our hypothesis.
What's the probability somebody's going to sign up and subscribe to our YouTube channel?
We could do that one next week. So let's set up a hypothesis grid. We did this last week as our P grid. It's all the probabilities from 0 to 1 in 0.01 increments. And we can go ahead and plot this bad boy relative to our D binomial, relative to our binomial distribution. So successes and failures, that's why we're using the binomial distribution. And there we see a very long tail on the left. And we see that our probability is centered right around 80%. And we see some uncertainty there, which is good. Uncertainty is what we want to know about when we're talking about this player, especially with small samples. So we have some issues. One, we can have a ton of potential hypotheses. I mean, one hypothesis is that players on average are 65%, but we could be multiple different hypotheses. One hypothesis, we could be believing that this player maybe is or isn't better than 80%. Maybe it was a total fluke. One issue is that the probabilities don't sum to 1, so they'll violate a probability distribution. So if we summed up all of those D binomes across our probability grid, it doesn't sum to 1. And then another issue, which is probably more pertinent here, is that when we're dealing with proportions, so successes divided by totals, we end up with really weird beliefs about our observations when the sample size is small. So a half, 1 out of 2, is not really the same as 50 out of 100, which isn't really the same as 500 out of 1,000. At 500 out of 1,000, we're probably more certain about what we're looking at than if we saw something happen 1 out of 2 times, right? 50% of the time. Even though those are all 50%, one of those has a lot more certainty. So enter the beta distribution. How are we going to help ourselves here? The beta distribution represents a continuous range of values bounded between 0 and 1. So this is a probability density function. Remember, we talked about probability mass function is going to be for discrete outputs. So is it 0%? Is it 20%? Is it 50%? Is it 60%, 80, 100%? The beta distribution gives us an actual density. It could take any value. All the little minutia values between 0 and 1 can be summed up with this beta distribution. And the beta distribution represents what's referred to as a conjugate prior for a binomial distribution. So what is a conjugate prior? A conjugate prior are prior distributions that allow us to produce a solution without integral calculus, which is in the denominator of the Bayes theorem. And so the Bayes theorem, when it's written out with integral calculus, can be really ugly and really difficult to, it's like super not approachable. But the conjugate priors, and we'll talk about these for normal distributions and count distributions going forward. This gives us a really convenient shortcut to update our prior knowledge with new observations. And it's especially useful when we're dealing with small numbers of observations like we have here. So the beta distribution takes on 2 parameters, an alpha, which is the number of successes, and a beta, which is the number of failures. And then to get the average, we just do alpha divided by alpha plus beta. So alpha divided by the total number of observations. So we have some prior knowledge that we believe players are about 13 out of 20 success rate in this drill. So we're going to use that as our prior. So we set up a prior alpha, which is 13. And we set up a prior beta, which is 20 minus 13, or 7. And again, we can calculate the prior average as 65%. And now we set up our hypothesis grid, 0 to 1 by 0.01 increments. And we can go ahead and plot this using the d beta function. So we're passing this function our probability grid. And then shape 1 is the alpha parameter. And shape 2 is the beta parameter. And when we run this, stretch it out. We get a cool looking chart that shows us our probability mass, our probability density, right underneath 65%, and then some level of uncertainty within that distribution. Okay, so now we return to our primary question. How are we going to use this to see how confident we are that this is an 80% shooter, that this individual is 15% better than the average tryout player that we see? So we start with that prior knowledge, our prior alpha and beta, and we're going to update that knowledge with these observations. So we gave the player n equals 20 attempts. And we observed out of that from our original data set 16 successes and 4 failures. And so updating the prior to get a posterior when we're dealing with this beta conjugate universe of Bayes is a simple addition. All we're doing is we're saying, give me the prior alpha and add it to the number of successes, and give me the prior beta and add it to the number of observed failures, and now calculate a new average. Posterior alpha divided by posterior alpha plus posterior beta tells us that this person is probably somewhere around a 72.5% shooter. And what we can see here is that what we did was we started with a prior, we observed some data, and we shrunk that data closer to the prior, but not all the way. So we basically said, we've seen some information, we think this person is better than average. we're not ready to say that they're 80%. We're not ready to say they're 15% better than average, but we do feel like they're better than average given the small sample that we've seen. So it shrinked it down towards that average, but not all the way. And there's some uncertainty around this. So we can use a simple calculation of variance by multiplying the alpha and beta and then dividing by the alpha plus beta squared multiplied by the alpha plus beta plus 1. And we know from our stats that variance, if we take the square root of that, produces a standard deviation. And now we can use the alpha and beta to also produce some quantile intervals, or if we wanted to calculate confidence intervals, or what in Bayes is called credible intervals, which are slightly different than confidence intervals in the way that they're interpreted. We can go ahead and calculate those. So there's our quantile intervals, and we can now plot this data. So we can actually use the d beta function and simulate from the posterior alpha and the posterior beta. And what we're going to get is a little bit of an observation with some uncertainty. So we'll see the probability density is under that 72.5%. And we see some uncertainty. And then we see our average of our population is right there in the blue dashed line. So we can see that the distribution has started to shift. So let's say, man, we really want to be certain about signing this player. So let's give them 20 more attempts. So we want to make sure that what we observed wasn't a fluke. And in the next 20 attempts, they get 17 out of 20. So actually even slightly better. So let's update our knowledge. And since we're doing Bayes, as we talked about last week, we don't have to recalculate the p-value and say like, okay, now that we've observed 17 out of 20, what's the p-value given our hypothesis of 65%? We actually take that data, we take the information that we learned from our prior posterior, and we make that the new prior. And we're saying this is what we think about the player now, 72.5%. Go ahead and update that with the new observations of 17 and 20. It's all the same steps. We calculate the estimated standard deviation, or the estimated average first, which is about 77%. Then we calculate our our variance, and then take the square root, and we calculate our standard deviation. We calculate our quantile intervals for 90% using the Q beta function. All right. So now we see that the probability is on the low end of that 90% confidence interval is actually better than the population average. And now we'll plot all three of these distributions and see how updating has allowed us to change our opinion on the player. So now the red is our most recent observation of this player. The green was the first 20 shots, and the blue was our best guess at what the player would be just walking in the door. That's our base rate. It's our prior. It's the best guess that we have after not seeing any data. And the cool thing about this is you could literally do it after every game. You could literally do it after every single shot. And we did a prior episode, which we should link to, on this idea using volleyball data and win percentage of some of the female volleyball teams. And we used a funnel plot to show after every game how they start out and they have some wins and losses, and then it slowly starts to converge to a win probability that's individual to that team relative to the population average. And the more observations we see, the more that prior knowledge begins to drown out. And we say, you know what? This probably is the next Steph Curry. They probably are about a 76% shooter or something like that within the context of this drill. And selecting the prior here before we depart this 100 episode, selecting a prior here is important because you can set it from prior research, you can set it from prior observation, prior knowledge or domain expertise, or you could estimate it in what's called an empirical Bayes approach, which we didn't talk about here, but we did talk about in the volleyball episode where we used what's called moment matching or method of moments to estimate the alpha and beta parameter, and maybe we'll review that in a later episode. But that is how you use the beta binomial conjugate distribution to update observations, and you could do this in real time with any sort of outcome right now, and we'll talk about rates and normal distributions going forward. You could do it with any observation that's a probability. So pull any data, shot logs from NHL or basketball or field goal kickers or soccer goal, whatever it is, anything, and just try and get a sense for updating your knowledge with every single new observation.
Yep, exactly. So it'd be kind of cool to see how it like wiggles and wobbles as they improve and create like a plot about that. I think we might do something along those lines in the future.
Yeah, yeah, and I think you have a package that we can use to do something like that.
Yeah, we'll see.
Which would be really cool, right? Because it could give us a really cool way to observe how this data unfolds. I think a fun one would be actually looking at it relative to some sort of record being broken, like the home run, like Sammy Sosa and Mark McGwire going for the home run race, and what's the probability they're going to break it? As the season goes on, and you see more observations, and they hit more home runs or something like that. Would be kind of fun.
That'd be interesting. Let us know down below if that's something you'd like to see. We want to hear from you all, because this is how we've gotten to 100 episodes, is we've taken the feedback that you give us, and we try to update it and make sure that we're giving you what you're wanting.
Yep.
So with that, I think we can call it. I think we've learned a little bit more about how to apply Bayes' theorem using the beta binomial conjugates. And doing that. So thank you all so much for joining us. As always, my name is Ellis Hughes. You can find me on Twitter at Ellis_Hughes.
And my name is Patrick Ward. You can find me on Twitter at OSPPatrick, and at Tidy_explain is where you can find both of us on Twitter, and tidy.explained@gmail.com is where you can find both of us on Gmail, and you can open up an issue on the GitHub repo, or you can like and subscribe on the YouTube channel and drop any comments or questions below. And we do have a Patreon page, and we appreciate everybody that, if you like our work and you want to support us, we appreciate everybody that supported us through 100 episodes, and it's been pretty cool. And let's see if we can do maybe 100 more.
Let's see if we can do it. All right, thank you all so much. Keep on exploring your world.